welcome everybody. Thank you for coming to the last session and for coming here rather than going home to make yourselves look beautiful in readiness for this evening's big dinner. My name's Melanie Pankhurst and I work in PR for Dante, and I also look after the sort of PR and promotion activity of the new Géant project. And today we're looking at obviously monitoring and management of multi-domain networks, and the three speakers that you're going to hear, each of them are going to look at three solutions to the different and complex challenges of providing operational support for network services. First of all, we're lucky enough to have Matthias Ham, who stepped in at short notice to replace Gloria Vuahin. I'm sorry, Gloria, who is unable to be here today. He's been a software engineer and project manager for the IT industry for many years, but now he's joined DFN and works also in the Leibniz Supercomputing Center, and he's involved in the Géant project. So he's going to talk about iShare, the support tool to help management of network operations in a multi-domain environment. So thank you, Matthias.
Thank you for an introduction. So I want to talk about the work we have done in the now finished GN2, and we are continuing in GN3. First, let me introduce a short genesis of the work item called iShare. So iShare, the acronym, it stands for Information Sharing Across Heterogeneous Administrative Regions. And it was a work item of the GN2 project, started not earlier than in the year 4, that means at September 2007, with participants from DFN under the lead of GAR, and with the participants from PSNC, Renater, Red Iris, and Switch. So the scope of our work was that we gained the insight that there is a lack of support in GN2 for network operations management, especially in multi-domain environments. So our goal was to collect requirements, to describe use cases for a tool to dedicatedly support such operational processes. There were a set of basic requirements we had to face. So even if we have a multi-domain environment in Géant, the users of the services, they want to have a single point of contact if they want to order a new service instance, if they have problems with the services. So they want to have to bother with which NRANs are really involved in delivering their service instances. They want a seamless operational support. Of course, a tool like iShare has to support various processes spanning the service lifecycle, beginning from order of a new link, setup, provisioning, to fault management and change management. And of course, if we want to develop a tool, it should minimize the time and human resource needs and save time for the operational people. The last requirement is has a special meaning in the multi-domain environments, that even if we have a single tool, we have to preserve the autonomy of the participating NRANs. So they have to be the possibility to have their own incident management or whatever processes they have in their own domain, to have the processes as private processes as before, and taking and using the iShare process just for the multi-domain services. In the end of GN2, in 1.5 years, roughly spoken, we have reached some milestones. So we made a full documentation of the relevant operational procedures, of course only multi-domain operational procedures, and we developed a fully functional, also limited prototype. An ongoing work is the deployment of this prototype to the participating NRENs and to retrieving feedback from operations people about experiences with that prototype. This is currently done in these weeks. In our work, we were faced with two key points. One point was, even if we want to develop a tool to support the processes, we need a clear description of the processes we want to support, of course. We need a well-documented and unambiguous definition of the processes, which is agreed among all the domains. And the second key point is that the most important thing is to have a good information sharing between the partners. The relevant experts have easily been identified in case of errors on certain service instances. Technical data has to be at hand if it's needed. So let me first elaborate more on the first key point, the clear procedures. So our focus were the multi-domain services in GN2. So now one can ask what mandate has a little activity like, or little work item like iShare to define these procedures, and to tell operations people how to do their work. So we neither has the manpower nor the authorization to do so, but on the other hand, we need a clear description of the procedures. So our idea was to just document processes together with NREN operational people. So we have not constructed new processes, we just documented them. We described a set of 8 procedures and selected a single service named end-to-end links. So this is a dedicated point-to-point multi-gigabit network service used mostly for LHC OPN links and others. And this service was lacking most support, so we focused on this service in our work. So the first process was, of course, the process of sharing the basic administrative domain contacts so that the neighbors can speak with each other, have the contacts in the tool. Then we have the process-specific processes, the ordering, firstly, of a new end-to-end link, the setting up, technical setting up of a link, and then if the link is up and running, managing of faults, maintenance, change management. And if all these processes are not working well, then we, of course, need troubleshooting and escalation procedures to clear the situation. All these processes are in the deliverable named here at the bottom of the slide. So I will not elaborate, get in more detail with the process. If you want to have more information about them, you can read them in the deliverable or, excuse me? It's not accessible. Okay. Okay, then I will upload it, if it's possible, to the conference system. I think we can upload additional material there. Okay, sorry, I haven't checked if it's really accessible publicly.
If it is a public document, then if it's not there, then we'll have to make sure that it is.
Of course. So I will not focus on the procedures of the content of the procedures, more on the methodology we used in iShare for documentation of these procedures. So we had at first a couple of meetings with operations teams of several NRENs, where we first defined the basic roles and activities, and we had to separate which activities are private to each NREN and which activity are public in the sense that they affect the whole multi-domain end-to-end link service instance. And we concentrated, of course, on the public activities, and the private activities are left to the NRENs, how they define them. After that, we modeled the process using UML activity diagrams, producing these nice diagrams you see below. There was a need to define some special conventions how to produce these diagrams to get them as concise as they are. We had the rule of thumb that one diagram should fit on one page to get it clear, so that one easily can capture the process. But therefore, we needed to define some notational conventions. Based on these process descriptions, we identified the informations which have to be exchanged during the processes. So which piece of information is needed at which stage in the process. And of course, as we don't have the mandate to define new processes, we get back to the NRENs, discussed our results, made a review and agreements to check if we had described the processes correctly and not just produced new procedures which are not related to our current operational work. Now to the tool, to the iShare tool itself. The tool remains on separation of duty, that the domains are responsible to provide their own local data, of course. They have to provide it once. Administrative data, technical data, etc. And afterwards, they are in duty to keep the data up to date. Of course, we have a uniform way to propagate and publish data. We defined an XML interface. But of course, the domains are obliged to provide data in a timely manner. So that our tool, the iShare tool, can collect the domain data, aggregate, and give a tailored multi-domain view. So each domain delivers its own local view, and iShare tool then presents the overall end-to-end link information. This tool is accessible, the data is accessible only by the involved domains, of course, not public to all. The current focus of this iShare tool is the information exchange. And our more automated workflow support is left as future work because the more pressing was to have information exchanged, the information exchange supported. Here's a first architecture draft of iShare. Hope it's readable on the slide. We have a layered architecture. At the parts below, we have the domain components delivering domain data. They could be either legacy NREN information system or network management systems, or a dedicated iShare domain part, which publish the data over an iShare XML domain interface to this multi-domain component, the iShare central server, which then stores the multi-domain data. In future, more elaborate and more workflow management related modules can be added on top of the iShare central server using the iShare multi-domain management interface, also an XML-based interface. Of course, to deliver a prototype in this short time, we had to do some restrictions, to define restrictions. So for our prototype, we decided that we want a fully operational tool, operational people can use, but we had to reduce the functionality to support only a single procedure, only the end-to-link ordering procedure. And of course, a simplified architecture. So the prototype has only two components. The colleagues from PSNZ done the implementation work. So we had an iShare domain. We have an iShare domain part where the domains can publish their data, and we have a simple version of this central server. And we have a nice web GUI, which I afterwards show. The scenario iShare now in the moment supports is that a user or institution needs a new end-to-end link, needs to have a new one, and contacts its connecting NREN to place an order. This is the point where the ordering process starts. In iShare, a new end-to-end link request is created, and under the request, all information concerning this new end-to-end link is collected. Then the end sites have to submit their details to iShare, contact details, etc. An ordering coordinator is appointed. The ordering coordinator has the responsibility to look after the rest of the process so that it doesn't get stuck. It has not to be a member of the connecting NREN, could be a member of another NREN too. Then the route finding for the new link starts. And during the route finding, all information is directly documented in the iShare tools. Of course, the neighboring NRENs discuss with each other about the specification of interfaces, but they document it all in the tool. And at the end of the process, an offer to the user is made. So let's have a short look at the prototype. The first form is the list of requests, just a list of the known requests in the moment, together with some indicators of the current action status. So the icons show all the actions or some of the actions that already have been done. This is only set manually by the ordering coordinator, so no automated support for setting these status. With the add button, a new request can be created. First, the end-site information has to be entered. There's a general end-site section, end-site information section with organizational info. We have administrative and technical contact data. If this information is complete, we can then proceed with giving information about the end-to-end link itself, to have the details about the requested end-to-end link. So, for example, the requested ready for service date, the estimated delivery date, of course, the bandwidth requirements for the link, and the project the link is used in. When we have this information in the system, the actual route finding can start for the link. This is a manual process, so it's not, if you know Autobahn or other automated path finding systems. For this type of service, it's all manual stitched. So the route starts with the two end sites, we know, and we know also the connecting domains. And during the route finding, additional transit domains can be entered manually via this icon. And subsequently, the whole route of the link will be in the system, as you see here. Additional to this high-level view, we have, of course, detailed information about the interfaces. So if you click on such a triangle, you get full information about the interfaces. In addition to that, there's an action logbook where users can document actions they have done on the link so that everyone has the same set of information about the actions done already. So that's a quick look at the prototype. Now let me come to the conclusion of my talk. In iShare, we tackled the challenge of multi-domain operational processes, how to support the management of new multi-domain services. And we created a methodology which is applicable not only for the single service we have taken as a scenario, but also to other scenarios, because this is a general challenge how to document multi-domain processes is not only a Xi'an challenge. There are also in the research and education, networking, other scenarios around, which probably can use the same methodology or at least have the same problems to solve. So probably this methodology is one of the things which can be reused mostly of our iShare work as by now. With an iShare tool, we gain an increased interoperability in the multi-domain environment for non-automated processes. iShare fosters information exchange and the effectiveness of the operational processes. And the ongoing work now, it's lots of things to do, of course. We have deployed our prototype to several environs, collecting feedback, and want to gather more operational experience with the tool and discuss further requirements and possibly broaden also the scope of iShare to other services. And thank you, and if you have questions, feel free.
Well, thank you, Matthew. Are there any questions from the audience? And the only thing I was sort of wondering is what sort of feedback you actually had that was going back into, I suppose, develop it further?
So it's, you mean feedback from installing the...
People have used it already, the prototype.
So we have two kinds of feedback. One is about the prototype itself, about the installing and usage. And second type, of course, is about the usage of the prototype. But there is the problem that there is not as much operational experience with the tool in the moment that we can give really answers to the suitability and usability of the tool.
So when it goes out to more, then you get more data back?
Yes, that was our aim, to have a functional prototype people can use, can play with, so that they can give us feedback.
Are there any questions at all? Or we'll move on to our next speaker. Thank you very much.
Thank you.
So now, Martin Volsky works at PSNC. He's head of the advanced data management team there, and is working on the GEON project. He worked on GEON 2 and is now working still in the new GEON project. He's going to be discussing the issues involved in modelling and interacting with real-life network, and how CNIS is going to assist in that. Some of you may have already seen the demo Martin gave with colleagues earlier today after lunch, and hopefully this will also expand on that and help you understand further. Thank you.
Thank you very much, Melanie, for introducing me. Let me change the presentation. How to switch to full screen, because I don't know the Spanish language.
Sorry.
How to switch it to full screen? Okay. Thank you very much. And first of all, I'm glad to be here, and I'm going today to describe the Common Network Information Service. In particular, I will focus on modeling and interacting with real-life network, and I will speak on behalf of 3 other people who wrote the paper for this conference. These are Maciej Obensky and Cezary Mazurek from PSNC and Anand Patil from Dante. So I'm going to describe you today how the idea of having a virtual network model, which is a global view of network topology, evolved into the project. In particular, I will tell you, I will present you the virtual network model, which we designed and developed for the CNIS. Then I will give you some general overview of CNIS as a unified repository of all the relevant network information for a single administrative domain. I will provide you some information about the interactive with real network, because we recognize that the ability to collect information about the network topology from devices in an automatic manner is a key factor to widely adoption this project, this solution. And finally, I will describe how we evaluate the project by making CNIS deployment. So first, let me start with the motivation of CNIS. So what was the idea, what was the background to start off CNIS? So in Gen2 project, there are several applications that need to be aware of accurate network topology information. These are, for example, AMPs that needs precise network topology information to handle premium IP requests, or personal CNN tool to display the information about measurements on a set of hierarchical maps. The other application, like Autobahn, needs information about network topology in order to handle bandwidth on-demand requests. And in the beginning, these applications implemented the network topology model on their own. In other words, each application used its own network topology database. And this solution revealed quickly several drawbacks, like duplication fault, increased load, data inconsistency. So the idea of CNIS as a unified repository for a single administrative domain came up. And CNIS, we expected that CNIS will provide several benefits. For example, it will act as a single point of storage. It assures the automatic population of network database, seamless access for network information data stored in the database, and some advanced sanity checks. So that was the motivation to start off the CNIS. And first of all, we initiate our work. We started with the modeling of the network topology, because it was recognized as a key point to adapt all needs of future services that will interact with CNIS. So to model the network topology accurately, we made some assumptions for this model, and these are, for example, we assume that this model will introduce some generic elements. So in other words, we can view a network as a set of nodes, ports, and links. Then network infrastructure can be divided into several functionally consistent parts. We assume that the relations between particular network elements should be modeled, and we should keep the layer autonomy. And of course, we viewed and investigated some other existing solutions, some other existing approach to model the network topology. And these were, for example, the DMTF SIM network model, a very comprehensive description of network topology, and the language and an ontology for describing the network, and NMWG format. In parallel to design the network informational model, we started to collect user requirements for CNIS, and we quickly recognized that these requirements conformed not only to the implementation but to the database, to the informational model as well. And for example, we identified and gathered the requirement for historical data, so the CNIS informational model should support historical topologies, future topology. This model should record information who modified the data. We assume that there shouldn't be any direct or hard-coded relationship between technology-specific tables, and the model should be flexible. It means should allow to model the tunneling functionality. Finally, a CNIS informational model has been designed, and it was a joint effort of several NVNs. It would be hard for me to provide you the whole schema today and to describe it because it's quite complex. It contains, for example, 75 entities in relational view. So let me just give you a brief overview how it looks, displaying this logical view of the CNIS information model. As you can see, it consists of several parts. The main part of this model is the common schema, which stores characteristics common to all protocols and network technologies. And there are several technology-specific parts, like IP, Ethernet, or SDH, which inherit somehow from the common one. And the idea of such division is that we would like to keep the schema flexible, and we would like to keep the ability to add new technologies, for example, to the schema without necessity to reconstruct it at all, the whole schema. That's all as regards the CNIS informational model. Then let me go to the next point of my presentation, so interacting with the network. As I said, it was recognized as a key feature to wide adoption of CNIS in NVNs. And we assumed that we made two important, significant assumptions for the interacting with the network. First of all, we assume that CNIS is meant to manage infrequently changing part of the network information. In other words, static network data. What does it mean? It means that our CNIS doesn't collect information, for example, about the link occupancy, because this could be treated as a real-time data. And automatic topology discovery is based on a pull method, which means that CNIS asks or gathers information connecting with network devices and not the opposite way. So we don't assume that network devices will inform CNIS somehow using, for example, SNMP traps. Data flow in CNIS. So the key point of CNIS, as I mentioned, is the ability to collect the network information, the information about the network topology in automatic manner. And that's why we implemented the separate module for it, which is called CNIS Network Discovery and Management Application. And it is part of the CNIS management application. So CNIS management application is marked here. It's pointed with the pink, let's say, color or orange color. And CNIS management application is a web tool dedicated for network administrator to manage the network topology information. And this is a screenshot for this application, and it includes CNDMA. It includes a module to gather network information data automatically. Besides, CNIS exposes several interfaces to retrieve the data from the database. And these are, for example, topology service, which serves data for personal specific information. Then we've got Pathfinder for AMPs, and Autobahn service, which serves network information data for Autobahn. Just a brief overview of the CNDMA, Network Discovery and Management Applications. It is a part of the CNIS as a software somehow, but it's also a framework which can be extended by means of plugins. Because we quickly recognized that it would be even, let's say, impossible to provide to support any network topology, any network technology to support any network device. That's why we proposed the extensible framework for third parties that could customize it and extend it with the means of plugins. And plugins plugins, we can say, are specific for technologies. And plugins can be extended by means of drivers. Drivers are the components which interact with specific network devices. And CNIS delivers 3 sets of plugins for IP, Ethernet, and SDH network topology discovery. IP plugin additionally is equipped with 2 drivers for Juniper and Cisco routers. This is a brief screenshot for CNIS management application. As I mentioned before, it's a web tool dedicated for network administrators to manage the network topology information stored in CNIS. In particular, network administrator could manage the data manually, or he or she can launch automatic network discovery. Okay, so let me tell you a few words about the deployment. So it's in fact CNIS evaluation. During Jan 2 project, we finished the pilot deployment on Jan network. You can see the screenshots of this network here. And additionally, we accomplished several test deployments in DFN, FCCN, GAR, HENet, HungerNet, and Pioneer. As regards Jan 3 project, we are going to move towards operation deployment of CNIS in several NANs, in Bren, FCCN, HENet, Pioneer, and Red Iris. Okay, I mentioned about Jan 3 project because CNIS activity started in Jan 2 project, and then it is continued in Jan 3. And CNIS is a part of the Jan network service delivery platform. Because the idea is to bring all several tools that the development started in Jan 2, bring them all, and in order to support multi-domain workflows. And this is the aim of Jan 3 SA2 Task 5, to develop and maintain tools that help to create workflows to support multi-domain services. And at present, the Task 5 portfolio consists of 4 tools: ARMS, Autobahn, CNIS, and iShare. And we assume that this portfolio may change in future, so new tools may be added or existing ones may be retired. And there are several participants involved in this task: Bren, Dante, DFN, GRNet, GAR, Magnet, Bren, NIRF, PSNC, Pioneer, Red Iris, and Switch. To To sum it up, we can say that the unified model of a computer network for a single administrative domain guarantees reliable operations of network and services. We also learned that interacting with a real-life network and automatic data gathering is an essential aspect of wide adoption of a network repository. And that as regards the future directions, so first of all, CNIS, as I mentioned, will be developed as a part of the JANT network delivery platform within the within the scope of JANT 3 project. Additionally, for the CNIS as a tool, we recognize the idea to go. We assume to go towards standardization for data exchange model, for example, NML, NSI, or YANG. It will be investigated soon. And we recognize the necessity to, or necessity, we think of delivering CNIS as a framework. So in other words, we saw an idea to build CNIS with, or to deliver a CNIS with a set of software components. For example, a component for network topology discovery, a component for network data model. And depending on the future IPR for source codes, these components can be adopted somehow in various scenarios, can be moved or can be transformed somehow and used in other applications that needs, for example, the network topology discovery or network data model. If you would like to get more information about CNIS, you can go to the interim JANT 3 project portal, which is accessible for JANT 3 participants only. But there is a web page dedicated for CNIS maintained by PSNC, and it's freely accessible. Additionally, there is a CNIS development site which contains all relevant information and resources concerning CNIS, for example, binaries, up-to-date documentation, FAQ sections, but it's also available for JANT 3 project participants. If someone is interested particularly in CNIS database schema, he or she can download and review the deliverable, which I think is freely available from the JANT 2 portal. Today, there was a CNIS demo provided by my colleague Maciej Łabęcki, and I hope that some of you had an opportunity to be there and saw CNIS in action. For those who were not be able to, who was not be able to join it, CNIS CNIS demo will be shown on Dante booth. There is a mistake here. It is stated here that it is Tuesday, but the demo will be also shown tomorrow on Thursday at 11 o'clock on Dante's booth. So anyone who would like to get more information or provide some comments about CNIS could attend this demo. And that's all what I was going to say today. So thank you very much for your attention. And
thank you very much. Are there any questions that we have? This one?
yes.
Thank you.
Well, I wanted to ask if You mentioned up there that you wanted to at some point start working at least with the OGF network modeling language working group. So what's interesting in how much work you've done already when applying those techniques and tools that NML already has exposed, because it seems that your approach is quite different from the NML approach. So I'm interested in hearing about your views and how difficult it would be to change that approach, or if that would just be an interface to what you're doing.
Okay. I should say that from our perspective, we distinguish between a data exchange schema and between data implementation model. So what I presented here is rather a data informational model that serves CNIS as a base to store the network topology information. And what we are going to do is to provide complete interfaces with some recommendation, like for example NML, and to support and to provide the for example NML compliant interfaces, so to support compatibility with these recommendations.
Right, so it would just be for exchange. You weren't going to use the NML type approaches to describing your network yourself. You would use that as a data exchange.
Yes, that's right. So I would say that we will do some transformation when, for example, obtaining data in NML format and then store it into our own internal model.
Thank you.
Any other questions from anyone? So I also wanted to, thank you very much.
Thank you.
I also wanted to say,
Only one comment to this. Don't you think that it makes more sense if NML becomes a standard, to use the standard instead of having your own implementation or your own structure?
You see, when we started to design this information model, as I said, we investigated several approaches, several existing solutions, and we recognized that these solutions weren't sufficient for our needs, because what we've done in CNIS, what we have done in CNIS was to create a data information model that will fulfill all users, let's say, requirements, all applications requirements. And we recognize that the existing schema didn't allow us to do this, because as I mentioned here, there are several requirements for a CNIS information model, like for example, ability to store the past and future topology, or ability to audit data. And we recognize that it won't be possible to use an existing solution as it was. That's why we decided to distinguish between data exchange model and data implementation model, and provide compatibility on the exchange level.
Nevertheless, my point is you should extend the NML standardization to get things into the standard.
Yeah, perhaps it is one of the possible directions. That's why we started a cooperation with the people who are participating in NML activity.
There's also, in addition to the other sources of information up there about the CNIS development, there's a poster exhibition out in the hall, and there's a CNIS poster there. So you might want to have a look at that too. So our third speaker is Li Zhu, who is a PhD student in Amsterdam, University of Amsterdam, working on the Starplane project. And he's going to talk to you about his approach, or one approach, to the complex problem of pathfinding in multi-domain hybrid networks. So, welcome.
Hello? Hello? Yeah. Hello, everyone. My name is Li Xu, and I'm going to open my slides. Okay. Yes, everybody can see. My name is Li Xu again. I'm from the SNE group of University van Amsterdam. It's my great pleasure to stand here and share with you about our experience on declarative pathfinding in simulated multi-layer, multi-domain networks. I will try my best to keep all of you awake till like 20 past 6, I think. Okay. So, well, quick time. No picture. Ah, lucky, bad luck. Huh? Okay, so nowadays people are talking about the dynamic light path provisioning. So, in order to provision a path, the first thing to do is to find a path. So the challenge here for those resource broker or the system who provision the light path is to find a valid path cross domain which use different technologies and have different topologies. So our research question here is, can the difficult pathfinding problems in multi-domain, multi-layer networks be solved by a declarative approach? Why the pathfinding problem is difficult, I will explain it in a minute. And unfortunately, you can't see the picture. I'm not sure why, but okay. But this picture is it's a glyph picture which gives you the first impression of how hard the problems will be. Well, if you like, I will show it later. No problem. Okay, yeah, this one works. Thanks. So to make things clear, the domain here we're talking about is a group of computers and devices with properties in common and administered as a unit. And what is a multi-layer networks? So the official definition is a computer networks where the configuration of the network can be dynamically changed at multiple layers. So please look at this example. So here in this picture, we have multiple layers, Ethernet, STS, UTP, and also OC 1 and 2 layers. Those different layers composed of a network which is a multi-layer. After we all clear about what is multi-layer network is, so the next interesting question will be, and how can we describe the network and model the topology? So our solution is the network description language, NDL. I'm very glad that in the previous talk, the author mentioned NDL already, so thank you. And here I'm going to introduce you a little bit more detail about NDL. So NDL is a pilot research has been carried in our group for a couple of years, and it is based on the ITUT G805 function elements and the label concept from the GMPS. And the NDL creates the ontology of the network, and by using the resource description framework and the XML syntax. So the unique properties of NDL is that the technology independent, which means if I implement a pathfinding algorithm using the NDL property, so once, let's say 5 years ago, 5 years, in 5 years, a new technology pops up, then the pathfinding algorithm don't need to be changed once we're using the NDL description. Here is some examples of how the NDL looks like. On the left is the syntax of NDL. Here we define some subject and object, and also the predicts of the network. And on the right is the example code of NDL, which describes a network. So you can refer to the link below. So let's come back to the original problems, the pathfinding in multi-layer networks. Why it's difficult. To find the path in multi-layer networks is different from the single-layer network, where we can use well-known pathfinding algorithms like Dijkstra to find the shortest path. So a shortest path in the multi-layer network may be looped or not be a shortest one in itself. In next slide, I'm going to show a very simple, bad. It's give you the impression of how hard the pathfinding in multi-domain. And okay, I've already covered this one, sorry. Yes, and okay. Next example. Yeah. So here's a very simple examples we created. And two-layer scenario is an Ethernet over WDM. And here we have 5 devices. Device B and D are wavelength selective switch, which can forward a specific wavelength. So those two devices operate only on the WDM layer, while the device A, C, E are Ethernet devices, and which have interfaces operate in WDM layer at a fixed wavelength. Then the question is, if I want to find the path from A1 to E1. The simple solution is we apply the Dijkstra. Fine. Very easy, huh? Straightforward. So, but the question is it a valid path? The answer is definitely no. Because why? If you look at the interface A2, which operates at a certain wavelength, 1310 nanometer, while if you along the WDM layer and reach at the interface E2, that only operates at the wavelength 1550 nanometer. They are incompatibility. So the path we desired is not valid path. What are we going to do? First, we through from A1 we through A2. Then we first reach C4. An interface operates also at 1310 nanometer. Then we convert the wavelength to 1550 at device C, and go further till we reach E1, the destination. So you can clearly see there's a loop because we travel from B to D and back again. There's a loop in between. In this very simple example, there's also a loop created. So you may argue that, okay, if Dijkstra, we modify Dijkstra, it's also possible to have the pathfinding algorithm with these constraints like wavelengths, but we all know for sure a new approach is needed. And let's look at another real-world example. So in this example I show, here we have a star plane network, which is a research network, connects 5 supercomputer clusters in Netherlands. And the object topology of a star plane is a ring. So in this light path allocation scenario, first we request a path. We want to request a path from Vrije University. No work. Okay, from Vrije University on the top. Okay, yes. And also a path to the University of Amsterdam on the top left, on the top right, sorry. And then I also want to have a Vrije University to University Multimedia cluster. So I want to the request. Okay, I want to this two requests fulfilled at the same time. Then, okay, it's easy. Very simple. First, I create a light path between Freie University and the University of Amsterdam. Once, then, okay, because the path is already occupied, then in the next query, and the Freie University to the Amsterdam of multimedia have to go the other way around, so which go through the other two clusters reach its destination. Well, this is the first request. If we swamp those requests and have the request 2, we ask for the Freie University to Amsterdam multimedia first. Then we ask the Freie University to University of Amsterdam at the second place. What will happen? The clever shortest path, Dijkstra, will reserve a path because it's shorter, only one hop. So Freie University, Amsterdam, then to reach to the destination of multimedia. And we're not able to provision any path for Freie University to the Amsterdam University. So a combination of different requests will lead to a different result. That's what is the normal path-finding algorithm makes the result. So ideally, the same result is required regardless the order of the request. So, but is that true? So it's still a question mark. And okay, before I lead you to the declarative word, does anyone here has some experience on declarative programming? Please, can I see your hands? Declarative programming. Okay, quite some few. Okay, good. Then this slide is needed. So we are going to introduce a declarative approach. So for some background information, what is a declarative programming? So it's a kind of programming which expressed in logic of the program without describing the control flow as we or you get used to the interpretive programming. And as a subcategory of the declarative programming, the logical programming, which has 3 categories, subcategories. And the prologue one on the constraint programming is what we're interested in. And I should see all your hands raised up because you see, if you see the domain-specific language, like regular expression and CSS, I think everyone here has used that. And so again, the prologue. What is prologue? This is what the program is expressed in terms of rules, and executing is triggered by running some queries over those relations like rules. So why we are going to use prologue as a declarative approach in our path-finding algorithm? The initial idea was inspired by when we described the network using the NDL, and we just found, okay, it looks like we install the network information into database in a form of a semantic way. So once we have the database built, okay, I want to query on this database, just like we using SQL over some relation database. So we want to like a query-like language to explore the database, which stores the network information or topology, if you wish. And we found the Prolog or SWE Prolog, which is the implementation of Prolog, provides a bunch of libraries for RDF management and the semantic manipulation. They can load the RDF database and store in the format of triplet, subject, predict, and object. So you found when we describe the network in NDL, this is also what we use. So it's perfectly matched. So, and besides that, So the logical constraints, like the wavelengths, for instance, as I just explained, in NDL also can be implemented naturally in Prolog way, in logical. So it's logical reasoning, and moreover, the Prolog is able to reason all the alternatives of the query and is capable of handling complex query. Like, in this case, I have a query, a path from the same source to the different destination, while those two paths should not be the same. So I only express this in one line of the query instead of two. And also the development of the Prolog program is less complex than we implement imperative implementation of pathfinding, and it will provide a more flexibility on those various queries. You can define all kinds of query like this. And here is an example of the query, the Prolog rules and the queries. So on the big board, you see how we translate the NDL description to the Prolog rules. If you look at the red circle, here's a predict can switch to. It's a rule which implies while x and y x can switch to y, and those rules is defined by has an interface predicates from the NDL itself, and also x should not the same interface as y. So this kind of simple rules we created in Prolog implies the NDL description of the network. And in the bottom is some example queries, like I want to I want to have source A1 to destination E1, give me a path. Or another query like I want to source A1 connect all other destinations, give me all the possibilities, all alternatives. And the third one is the query like SQL select all. So it's giving me all the combination of the paths which is available in the network. And so the declarative pathfinding algorithm we've implemented is both hop by hop and layer by layer in Prolog. And what is hop by hop? Is from the source of the source nodes or source device, the hop means like we always try to find the nearest neighbors of its hop. And layer by layer means because we are handling multi-layer scenarios, so the source or destination will always be found first in the same layer instead of going to another layer, higher or lower layer. And the algorithm, the result of the algorithm is a list of the cross-connecteds that need to be fulfilled to make a valid path if the path exists. And the algorithm we've implemented is able to handle multiple or complex path requests, as I've shown just now. Okay, let's look at how the Prolog pathfinding works. First, we have a Prolog reasoning system installed in machine. Then we load the multi-layer network description in NDL, which is a database of the network. Then we load the pathfinding algorithm. Okay, then after this done, we are able to run any queries we like. Then finally we got the results. It seems like perfect world, right? No, because there's an important part missing. The multi-layer, multi-domain network description. Unfortunately, we are short of the real-world scenarios which describe the multi-layer network, especially in the NDL format. And also, it will be ideally perfect to have a scalable simulation platform for our experiments. So that's why we introduce here the multi-layer, multi-domain generator. So our goal is to generate the graphs that simulate real-life multi-layer networks with multiple technology, and also transform the graph, which is the node and edges, to the network description language, NDL, for both graphical network behavior analysis and for the multi-layer, multi-domain pathfinding. And the tools we choose is the Python network toolkit plus the network X library from the standard Python libraries, and also the Java uniform network graph framework. And since we are going to generate some graph, so the graph generation algorithm we choose is the Barabasi-Albert, which has the property of the scale-free network. And how to generate a multi-layer, multi-domain networks? It's gonna take me like another 20 minutes. I think time's over. And so I'm here. I just explain some basic routines of our algorithm to generate a network. First, we have generated some graphs at certain layers. Then we have repeated layers presents those multi-layer scenario, and we group these layers into a domain with some extra information like adaptation from higher layer up layer to the lower layer. And now we have a domain of which presents a simulated network, multi-layer. Then we repeat several times, and we got multiple domains. And then we apply the Barabasi-Albert algorithm to again to generate the interdomain links, which creates a scale-free network. Then the next step is to mapping those generated graph into a format of NDL. Then what we did is having every nodes at a certain layer have several edges. Each edges attached to the nodes we generate an interface. And for the cross layers devices like A, we got an interface at a lower layer and an interface at the upper layer, which belongs to the same device. And we repeat. Here we can generate some NDL description, which is a subject, predicts, and object. And we run some experiment and get some first step results. So we generated a variable size of 2-layer scenario multi-domain networks ranging from 5 nodes per layer per domain times 5 domains, which means the 100 nodes in total, to the 1,000 nodes per layer per domain times 50 domains, which means 100,000 nodes in total. And what we want, we'll run the pathfinding algorithm in, as I showed the workflow, and random select 2 pairs, one pair at source and destination, and apply the pathfinding algorithm over 100 times. And we want to evaluate first the average time of loading NDL and how long it takes to find a path. Here's some results. And on the table above is the number of triplets in which described in NDL. If you can see the right corner. And for the 50 domains, 2,000 per domain nodes, in total it's 100,000 nodes. We should generate like nearly 2 million triplets in format of NDL. And the figure below is an average time to load an NDL into a Prolog reasoning system. So we found if we load the maximum 100,000 nodes should take like over 2 minutes to load those information into the system. And I ran this over my laptop, and later on will be run over some clusters in parallel. And this is another example. The average time to find the first possible path using our algorithm. So if you notice this, we have the maximum, the 100,000 node scenario. It will take 4.5 seconds to find a path. And here, there's a bunch, because this is a pilot research, so there must be a bunch of future work which we can carry on later. So like if we introducing some labels as a constraints to the network we generated and apply the algorithm again, we got different results, I think. And also we could compare the efficiency to the other implementation of the path-finding algorithm, like Python interpretive path-finding algorithm developed by a member of our group, and some other future work. And the most interesting one I want to point it out is the declarative light path allocation in grid. So I've just shown an example of we want to allocate a light path with a complex query, or the order of the sequence, the order of the requests will be a matter of the light path allocation. So moreover, we want to optimize the network resource usage by using those declarative approach. So to conclude, so we found the path-finding in multi-layer networks is a complex problem, and we propose here a declarative solution for multi-layer, multi-domain path-finding using semantic network description, NDL, and a logical reasoning system, which is Prolog. And the third solution is we generate the multi-layer, multi-domain to simulate the real-world networks. And here's a list of the reference you can refer to if you're interested in this topic. And if you want to contact me or reach me, you can have this email, and also try Google Image people. I think I've done. Thank you.
Are there any questions from the floor at all? We've got time for a question if there are any before I launch into one. Is that all? Well, thank you very much for coming back and conversing us all.
Thank you all.
And I've got a couple of sort of announcements. One, I will repeat again about the buses, but first of all, unfortunately, one of the delegates' handbags has disappeared, and she's got a passport and iPhone and all the valuables in there. So could I urge you all to look under the desk? There's shelves under the desks, and if there's any bag there that doesn't belong to you or your neighbour, can you get it out and under the chairs? And also, if you could keep your eyes out for a small black handbag that is on its own, or is somewhere it shouldn't be, could you please have it into registration, or if it's later than that and there was around, bring it to the dinner and hand it into someone, please. So it's just a small black handbag, so it's kind of like every woman's handbag, really.